us a really detailed list of things you want us to learn, and we'll learn them. And then you test us on the material that you've outlined here, and like we'll just agree to like part ways here.
I once had a lecturer for transition lines where we were all so lost that he actually spent an hour doing the lecture and French and no one noticed.
Oh yeah? Did he notice?
After an hour.
It's like, was I just lecturing in French? You ever have a teacher write, like,
It's not that unusual in Canada, but it is here.
because we all speak French. Actually, like, most of us have functional French. They teach it to you for like 10 years. You're like, going to pick up something. But we had some teachers who would actually write, like, reversed, like, as a mirror. Because apparently in, like, old Soviet Europe, when you had to, like, they taught you to write on glass, you'd have to present, but, like, from behind the glass. So everyone had to learn how to write in the opposite direction. It's not as hard as you'd think. I'm like, I wonder how difficult this is to like write backwards, and I tried. It's like, you'd be surprised how like effectively we can do it. We had teachers who'd like spontaneously like switch to like writing in like the reverse direction. I'm like, oh my god, am I having a stroke? Am I having a stroke?
I had a lecturer once that was very keen on his subject, very enthusiastic, and when he got very enthusiastic, he dropped back into his original Arabic.
Oh yeah? Well, I'm not going to be switching languages. My French is not that good. And I'm not that excited about this material. Okay, so I think maybe we should start. So during my toot on Tuesday, we discussed that it may be helpful for me to go through the rules of logic more slowly and give you a better introduction to some of these symbols that we're going to be using. I feel this will both help in this course and Dr. Willis's side of things. So who has seen like the logical operators or, and, not? 1, 2, 3. Oh, most of you then. Okay, so like this should be more of a review. Okay, so when I say or, like, to mean the logical statement or, these ors are put in between statements that can either evaluate to true or false. So if I put an or between something, P or Q is only true, is only false if both things are false and true otherwise. Right? So this is like a multiplication table. Whoops. Oh boy. I don't want you guys like huddling in the back. Okay. So this is like a multiplication table. So this would be P across here and Q here. So P is true, Q is true, and true or true is true. True or false is true. False or true is true. False or false is false. And so this is how I remember this. You only need to remember the one place where it's false, and everything else is true. That's pretty easy. The next one is, examples. So 3 is greater than 7, or 7 is less than 3. True or false? True. Why? Next statement is true. Okay. Following one. 3 is greater than 7, or 3 is greater than 5. False. Neither are true. Right? Huh? Oh wait, they're both false, yeah? Yeah. Get out. No. Making me look bad. No, they're both false, and this was entirely deliberate. As I mentioned in the previous lecture. Okay, so the next logical operator is AND. In fact, this is actually not needed. AND is equivalent to OR with a not, but we just use it anyway because it's useful. So AND is only true if both inputs are true. So true and true is true. False and true is false. False and false is false. Okay, so when you AND something, both of the things that you're ANDing have to be true in order for it to be true. So I don't have examples for AND. Okay, not. This is the easiest one. It's just the opposite of the thing that you're giving it. And so the logical statement not is the negation of a logical statement. So not true is false, and not false is true. Have you guys seen these symbols for true and false? And it's the typical symbols for true and false. You can use T and F if you want, but you'll find that we'll be running out of letters really fast. So it's good to introduce symbols.
Is that the standard symbol for not? I've seen you just put a bar on.
Yeah, okay, so there's this interplay between logic and sets. So when you use a bar on top of a set, that's the complement of the set, which has some sort of relationship to logic. So I'm going to say no. You can also see like a tilde, like the squiggle used for not, but this is most typical. Yeah, so I wouldn't use bar. Yeah.
Or an exclamation mark out of C.
Exclamation mark out of C?
Yes, see the program.
Oh, okay, wow. Okay. Okay, so we talked a little bit about sets last week. So a set is a finite or infinite collection of unordered and distinct objects. Anything in between curly braces is a set, and the things inside the curly braces are called elements. A set's cardinality, denoted by these bars, or the number symbol, is the number of such elements that the set contains. Okay, so quiz, or example. This set has 6 elements. Right, so as you see, they're all distinct. Order doesn't matter. And there's how you'd write the set cardinality down. Okay. The standard sets that we talked about last week are the natural numbers, which are 0, 1, 2, and so on. The integers, which are the naturals, as well as the negation of the naturals. It used to be I for integers, but that was changed like in the last 10 years. Don't ask me why. The German word for number is anyone German in here? Thank you. What he said, Zahlen. It's a word for number, so that's why integers is denoted by Z. The rational numbers are all fractions with non-zero denominators, and we also discussed real and complex numbers, but we'll get back to those after this. Okay, so predicate. You know what a function is, yeah? A function takes in a number and it spits back to you another number. A predicate is the same thing as a function, except it takes in a logical statement and spits out true or false. Yeah, so in the equivalent in computer science would be like a Boolean statement. These are all Boolean operations. Okay, so the predicate has to be defined over some universe, right? You need to map from something to true and false. So here's an example of a predicate which tests for primes. Okay, so I could say P is a predicate that takes integers to true and false, and it's defined like this. Okay, so usually this is the domain, this is the range, and this is a symbol that means maps to. Okay, so x, which is an integer, will map to true if x is a prime and false otherwise. Okay, so P of 7, 7 is a prime, so it's true. P of 8, 8 is not a prime, so it's false. P of 101 is a prime, it's true. This is my favorite prime number, or number in general. Why? It's a prime. Its representation is a binary number. Do you know what binary numbers are? This is 5, which is also a prime, and it's a palindrome. And it's super easy to type. So, it's my favorite number. That'll be on the exam, by the way. Okay, so you've seen predicates already. We just sort of write them in a funny way. So the symbol in is read is an element of, and this is a predicate. Right? It's a predicate which takes, as we said, some elements in the universe, and it maps true or false. Okay, so we're gonna take an element in a universe, and we'll tell you if E is an element in that universe. Okay? Don't use this symbol. Okay, that, although is also, these are both epsilons. But this one is like the script version of it. And we reserve the script version of it for the calculus part to denote a number that's really small. Okay, so if we have a universe of even numbers, 2, 4, 6, and so on, 2 is in the even numbers if and only if 2 is an element of the even numbers, if and only if true. Right? That one's easy. 17 is an even number if and only if 17 is an element of the even numbers, if and only if false. Right? So when this is false, we typically just write that. It's not an element. Okay, so this is where things started to get a little bit more tricky. So we have these two other logical operations, existence and the for all. So these are called quantifiers. And the reason we need these is because the universes that we're operating over are typically infinite in size. So intuitively, what this exist x symbol means is that if there is an x in this universe satisfying this predicate, this will only be true if there is one of these elements of the universe for which this is true, right? So it's like appending an infinite amount of ors, right? So there is an x in ABC such that x is a. There is not an x in 1, 2, 3 such that x is greater than 7. And there is an x in the integers such that x is prime. Okay, so here's a question. Is this a true or false statement? There is an a and b in the integers such that a over b is the square root of 2. No. Why? Yeah, but can any of you prove it?
Can you prove it?
Yeah, it's quite easy.
It's because you know and when you bring it to
Okay, that's loosely correct. It involves like a GCD argument. Basically, you assume that you can do this. You can write square root of 2 as a reduced fraction. And then from that, you can show that the fraction that you started with isn't reduced. Maybe I'll make you do this on an assignment or something. But it's interesting to think that you're going to have to support these things that you say with arguments that are factual. This isn't like Reddit or Facebook. This is real life. Okay? Okay, so here's the other quantifier for all. And it relates to exists with the same sort of intuition. That we're just going to append an infinite amount of ands to these predicates. And so the symbol for all denotes for all, alternatively for every for each. And it's called the universal quantifier. And it is used to make or test assumptions universally over an entire set. Okay, so there is an x, or for every x in U, Px is true, if and only if Pu naught is true, and Pu1 is true, and Pu2 is true, and so on. Okay, so here's a more complicated example. Okay, so there's a predicate up there, Qx, and its definition, has anyone seen that before? 2 bar x. Okay, so this means 2 divides x. Okay, so 2 divides 4. 2 does not divide 7. Okay? So the way we can define this is 2 defines x if and only if there is some integer y such that 2 times y is x. Right? X is an even number. Only x is divisible by 2 only when you can express it as a product of 2 and something else. Right? So it is not true that every integer is divisible by 2. Why? Because there's odd numbers, right? You only need 1 to show that it can't be true. So 3 cannot be written as the product of 2 and another integer. Oh, I put the answer up on the board before I asked the question. So it'd be really bad if you got that wrong. Okay, what about this next question, which also has the answer? Okay, this is another predicate Rx, which is true if and only if... Oh, no, this is a different one. Rx is a predicate if and only if 2 divides x minus 1. Okay? So it is true that every x, which is an integer, either x is divisible by 2, or x minus 1 is divisible by 2. Right? Because either it's an odd number, which you subtract 1 from to get an even number, or it's even to begin with. Right? So this is a true statement. That's a false statement. Yeah, well, this is important, right? For every x, either one of these two things are true. It would be different if I said for all x, qx, or for all x, rx, maybe I should write this. I don't want to like undo all of this fantastically organized information. No, risk is this. There's a chance there are markers in there. I thought that was like something that they just leave. Are you kidding me?
Is there any good ones left? The other lecturers have taken.
Yeah, there are no markers. Whatever.
Can you draw it on a piece of paper on that? Here's no.
Someone bring paper?
I'm sure I can make that.
Okay, so we'll try this.
Young people today. I don't know. You need a pen. Visualize.
Thank God this guy's here, eh? I
Use
get
the controls on the visualizer.
Oh, there's an on button. That's a stupid design. Is focused?
Focus itself.
Are you focused?
No.
No. Okay, so we had qx as a predicate, which is true if and only if 2 divides x. Yes. Okay. We also have Rx is a predicate which is true if and only if 2 divides x minus 1. Okay. So i.e. x is divisible by 2 and x minus 1 is divisible by 2. Okay, so we do have for every x is an integer, either 2 divides x, or 2 divides x minus 1. Okay, what about this? For every x, an integer, qx, or for every x, an integer, rx. Yeah, right? So it's important to understand that there are subtle differences in the way that we can write these things. What about this one? Does there exist x integer such that qx? So this is false. Yeah, why? Yeah, this requires no explanation. 2. You need one element from the integers which satisfies it, right? So true, right? True. Because x equals 2 satisfies this.
Why doesn't the second statement work again?
This one?
Yeah.
Because one of these two statements has to be true. Neither of them are. Every integer isn't divisible by 2. 3 is not divisible by 2. And every integer minus 1 isn't divisible by 2. 4 doesn't satisfy this. Yeah. See, but it's important where this symbol goes, right? Because pulling it out made a big difference. Right? It changed it from true to false. Wow, this shows up here too. Computer. Anyone watch the IT crowd? All right, never mind. Yes, anyone? Yeah. Computer. Computer. They tell the boss that the computer's voice activated, and he spends like 10 minutes yelling at his computer to turn on. Okay, so here's a more complicated theorem involving quantifiers. So when you put a bash or an exclamation sign after existence, this means that the thing that exists is unique. There is exactly one of them. So is it true that there is a unique number which is divisible by 2? No. There's lots of numbers that are divisible by 2. Okay, so in particular, this is a pretty important theorem, which says there is exactly one set, denoted like this, with no members in it. This is called the empty set. And so there is exactly one set with 0 members. There is exactly one set whose cardinality is 0. Where's my shoehorn? Okay, so this is the correct symbol for the empty set, a 0 with a strike through. This is the symbol for phi. This is the symbol for phi. So make sure you write these differently. Yeah, I know they look basically the same, but yes. Uniqueness. So you read that statement as there exists unique empty set such that for every x, x is not a member of the empty set. Yeah. Okay, so here's some things that the empty set satisfies. For any x, x is not a member of the empty set. The empty set contains nothing. So you can ask if it is horse an empty set? No, nothing's in the empty set. For any set, the empty set is a subset of that set. You guys know what subsets are? Yeah. Right, so every set contains the empty set. Right? Even the empty set. For any set, if A is inside the empty set, then A must be the empty set itself. These aren't that important. They're just kind of interesting. So like these are the rules from which all of mathematics basically falls out from. And in fact, like all the rules of mathematics, you can derive from the fact that there exists an empty set. It's pretty cool. I'll be teaching your course next semester. Okay, so some operations on sets. Set difference, which is sometimes read A take away B, which sounds really childish to me, but whatever. It's denoted A minus B and is defined by this. Okay? So the set A, take away the set B, is the set that we build like this. All the elements Z, such that Z is in A and Z is not in B. Okay? We can also write it like this. Z is in A minus B, if and only if Z is in A and Z is not in B. Some examples. 1, 2, 3 minus 3, 4, 5 is 1, 2. Right? Because the first set we have to remove 3. Okay? What's this? 3, 4, 5 minus 1, 2, 3. 4, 5. Okay, so does this mean that set difference is a commutative operation? No. Why?
Because we already have an example where A minus B doesn't equal B minus
Yeah.
A.
If it was commutative, these two results should were obligated to be the same. Intersection. Okay, the intersection of A and B, denoted A intersect B, is defined like this. The elements of A intersect B are the elements Z, such that Z is in A and Z is in B. Theorem. Okay, so just another way of writing this. Z is in the intersection of A and B if and only if Z is in A and Z is in B. Right? You may have remembered drawing Venn diagrams. So in a Venn diagram, this would be the thing in like the middle. Okay, so the common elements between 1, 2, 3, 4, 5 and 2, 3, 4 are 2, 3, and 4. Okay, for any set C, what does C intersect the empty set? Empty set. Yeah, the only thing that those two sets share are nothing. Right, so it's true for anything. What's the empty set intersect the empty set? Empty set. Hey man, I asked these to third-year computer scientists in my old school, and like they all got it wrong on the exam. Maybe I'm just a terrible teacher. We say that A and B are disjoint when the intersection of the two sets is empty. So disjoint basically means that the sets like don't share any elements. Okay, so 1, 2, and 3, 4 are disjoint because they share no elements. But 1, 2, 3, and 3, 4 are not disjoint as the intersection is 3, which is an empty. Right? They share an element. Is A in the empty set disjoint? Oh, we heard opposing opinions. It is true that A and the empty set are disjoint because it satisfies that definition. Right? The intersection of anything in the empty set is empty. Right? And the definition of disjoint is that it is disjoint if the intersection of those two things is empty. So this must be the case, that A and the empty set are disjoint. Union, both. For sets A and B, the set union of A union B is defined by this. Z is in the union of A and B if and only if Z is in A or Z is in B. Right. Example. If A is A, B, and C, and B is B, C, D, E, then A union B is A, B, C, D, E. Right? It's the set of things that are in both. Right? So you can think of it as just putting all these elements into the same set and then like striking out the ones that are duplicates, since they don't count anyways. Okay, De Morgan's laws. Not going to have much time to prove these things, but they're true. A magician called De Morgan proved them. They're quite famous. And it tells you how these unions, set differences, and intersections distribute over one another. So it is true that the elements that are shared between A and B intersection C are the same as the elements of A intersection B union A intersection C. So you should draw some Venn diagrams to like convince yourselves of these things. Okay? So the elements that are both in A and the intersection of B union C are those in A union B intersection A union C. Okay. Those elements that are in A set minus the intersection of B and C is what is in the intersection of A minus B and A minus C. Okay. Well, lastly, the elements in A minus B intersection C is equal to A minus B intersection A minus C. Yeah, so they're both true. Obs. Maybe the last one's just that important that I need to say it twice. Yeah, I don't know why that those are the same thing. I probably missed one. That last one probably should be a union. So what would A minus B union C be? Homework. I don't have a pen, so you can write this down. Exercise. Right. What is A minus B union C? Or, just go to Wikipedia and type in De Morgan's laws, and it will tell you. Which is a totally valid way of doing homework, by the way. Like, it's called research. The first thing you should do before solving a problem is see if someone else solved it. It's very sensible.
In which case, since the question has already been solved, you don't have to do it at all.
Yeah, I actually got in trouble for this once. And I was pretty pissed at my professor. Okay, a little tangent. So I was asked to do a question, right? We have a textbook. And the question was like, prove such and such. So I read my book. I'm like, oh, okay, there's like a theorem in here from which the thing we were asked to prove on our homework is like a direct consequence of. So I'm like, okay, this is proved, page 31, theorem 2. Like set n equals 2. And so my homework got back to me. And there was a mark that was 10 out of 10. And that was crossed out. Then another mark of 0 over 10 was written. And then that was crossed out. And then there was a note written that said, after some discussion, we've decided not to include this in your assignment. I'm like, okay, why would you give us a textbook and then not allow us to use it? But I'll never do such a thing to you. If you find a source and you give it to me, that's a totally valid way of solving your homework. Huh? You don't have internet on your test, right? I don't know if your test will be open book or not. My preference would be to let you have all your stuff on your tests, because memorizing is sort of a waste of your time, I feel. But I'm not the course coordinator. What's your opinion on this? Huh? Whether or not you'd like for your test to be open book,
It's sort of unrealistic to not have your resources there just every other time. More likely you won't have your
that's how I feel, right? But knowing we also can't ask you throwaway questions if you have your books with you. I can't ask what is the definition of commutativity if you have your blanks. Anyways, we'll talk about this. My preference would be, my actual policy on this is that I give my students like basically anything that can plug in, and an infinite amount of time. Because I don't feel anyone should be forced to be hurrying. But that backfired once when I had to sit 7 hours in a room. This presumes that people will give up eventually. Ranges. Ranges are subsets of sets. These ranges can be open, as in brace AB, which means the endpoints aren't in the range, or closed, as in square brace A through B, where now the endpoints, that should be A and B, not A and A, are in the range. Or they can be a mixture of both. These are called Clopin, which is a portmanteau of opened and closed, as in those. Right? So this one does include B. This one doesn't include A. So I imagine you've been seeing these already in the analysis part of the course, yeah? Yeah. Okay, a little bit. Right, so they're just ways of expressing sets. Right? When you have an ordered universe, like the real numbers, you can say like -2 through 2. Interesting enough, we won't be able to do this for the complex numbers. I can't say, give me all the numbers between 2 minus I and 3 plus I, right? Because we don't have this type of, we have a plane of numbers, not a line. Yeah, right here. Okay, so here an example of ranges over the integers, which I can actually write out. So the range, 2 through 7 on the integers, is 3, 4, 5, 6. The open range. The closed range, 2 through 7 on the integers, is 2, 3, 4, 5, 6, 7. The Clopin range, open 2 through 7, is 3, 4, 5, 6, 7. The Clopin range, 2 to 7 open, is 2, 3, 4, 5, 6. Okay, test. Can you write the union of these Clopin sets as one range? Yeah, what is it? AB with square brackets, yeah? Because the union means we inherit the A here and inherit the B over here. Okay? What about this? Intersection. The open range between A and B. Because this means that we lose this B because it's not in here. And we lose this A because it's not in here. So you should think a little bit about how De Morgan's laws apply to these ranges, because this will become very crucial in the analysis part. Okay, so why have I been showing you all of these funny symbols? So you learned this the other day, yeah? Yeah. Let us read this. Suppose f is a real valued function with domain the reals and range the reals. And the point P and L are also real numbers. Then the limit as x goes to P of f of x is equal to L. And using everything we learned, I'm just going to read this. If and only if, which means if this is true, then this must be true. And if this is true, then this must be true. For any epsilon greater than 0, there is a delta greater than 0, such that x in this open range, L minus delta through L plus delta, means that the absolute distance between f of x minus L is less than epsilon. Yeah?
The L's there is minus delta, so shouldn't that be P?
Huh?
So limit as x goes to P, so shouldn't that be P minus?
Oh, yeah. Sorry. This should be P. It was funny, because when I was writing this down, I'm like, you should be very, very careful that there's not a mistake on this slide. So you'll look like an ass. Guess that's too late. Anyways. Good on you well, this is why Dr. Willis teaches this side of things. Anyways, the point is that these things can start becoming more meaningful by using symbols. That is my preference, because you can get more compact statements where I can see, where you can like delineate what variable is doing what. I think it's a little bit more easy to extract meaning from these operations with symbols. Right? But in any case, now you can do either. Right? Hopefully I did this one right. So for those who haven't gone to tutorial this week, this is going to spoil a question, I guess. Here's another way of writing something. Hopefully there's not a mistake in this one. So one of the questions was, write down a formal definition of the limit for x at infinity. So the limit of f of x tends to L at infinity if, for any epsilon greater than 0, there is a number, that's a real number, such that for any x bigger than that number, f of x is arbitrarily close to L. Right? So this basically means that if you have a function which is limiting to L at infinity, that means I'm able to choose, so it's a game, right? When you see this for all, an adversary is picking it. You don't get to pick it. So someone comes along and says, here's an epsilon, like 1 divided by 10 to 20 million. When you see this symbol, you get to pick it. Right? So okay, so some adversary gives you an epsilon. You say, okay, no problem. Here's an n, like 50 million, so that any x that's larger than 50 million is going to satisfy this property for the epsilon that you picked. Right, so this is how you should think of it. Right? Universal quantifiers, like the for alls, someone else is picking it. The existence, you pick. Right? And the statement is true if you can play this game and everything on this side is satisfied. Yeah? Okay, I know it's a little bit early for break, but we're going to take one because I'm going to shift to the teaching complex numbers again. Right? So just, yeah, it's a good place to take a break. So 10 minutes. How you going?
How are you?
Not too bad. Sure.
Is this right? Where is the word from 5, 7, and 11, isn't it? And does every row has multiple inversion? No.
Yes, because then every row should have a 1 in it.
Yeah. Since it doesn't have multiple inverse, everything doesn't have multiple inverse, it's not zero.
Yeah, because it would be obligated to have inversion if it was a field.
Okay.
Perfect.
And additive identity is going to be 12.
Yeah.
The additive inverse is going to be 12 too.
Yeah. Oh no, additive inverse?
Yeah.
No, not 12. Additive inverse is the thing. Okay, so the additive inverse of a number is another number, is the other number that makes it sum to 0.
Yeah. So, if...
How do you make 8 go to 0? Or how do you make 8 go to 12?
So, would that be itself? No.
Well, 4 plus 4 is 8. That's not 0.
Oh, hang on, because 8 plus 12
Is
is 8.
Yeah.
So, it makes it
8.
8.
You need to make it 0 though. Or you need to make it 12. 8 plus 4 is 12.
Yeah.
So the additive inverse of 8 is 4.
Yeah. So,
The additive inverse of 2 is 10. Because 2 plus 10 is 12.
yeah.
So like in the integers, it's easier to understand. The additive inverse of 3 is minus 3. Because that's you add those two things together, you get 0. But since there are no negative numbers here, it's 1 and 11, 2 and 10.
Oh, okay. So, would I just say that? Like,
Yeah.
everyone's got a different additive inverse, which is...
Yeah, you could say maybe 12 minus that number if you want. But that's the point, right? The point is the additive inverse is the other thing
Yeah.
that makes it go to 12.
Yeah. Yeah, cool, I got it. Thank you.
Huh? Oh. This is my solution for like dragging the board down. Huh? No, I got this for me. So I will be getting the bonus marks. Huh? I don't think it's necessary for me to like bring two boards down at the same time. I'd be like,
What if it's a better hook?
if it's a better hook, then yeah, I'll give you bonus marks. But this thing cost me like $1 at IKEA, which, factoring in the fact that I had to go to Tempe, makes it significantly more than. Yeah, yeah. Wait, but if this hook disappears, I'm immediately blaming you. Right? How about you take all of this energy that you're thinking about getting bonus marks and filter it into studying and just earning those marks outright? Yeah. Yeah, it's true. If you got me like a personalized one that had like my name engraved on it or something. Ah. So thongs in America are a type of underwear that have no acids. So this is really hard for me to like change the meaning in my head. Oh yes. Well, we have jocks too in Canada, like the thing that protects your groin. But we also call jocks those people in high school who beat up the nerds. Yeah. Oh, that's a weird thing to call people who beat up nerds. Damn underwears. Okay, do we have everyone? Irrelevant. I'm starting anyways. Yeah. My favorite. Okay, so a recap of last class, where we learned about a new number system called the complex numbers and how arithmetic is done on those new numbers. So a recap of the arithmetic: if you have two complex numbers given by z0 and z1, their sum is given by the first equation up there. So you add the real parts and you add the imaginary parts. Their product is given by the second equation, which is just the result of doing cross multiplication, where you remember that I squared is minus 1. And inversion, after some effort by all of us, we came up with this equation, that the inverse of z0 is its conjugate, which we haven't defined yet, over x squared plus y squared. Okay, so something I wasn't able to define last class because I ran out of time is the complex conjugate of a complex number. And it's denoted z bar, and it's given by this statement. Right? So if z is x plus iy, z conjugate is x minus iy. And an example, the conjugate of 2 plus I is 2 minus I. Here are a few statements that are true about conjugates. If z is x plus iy and another complex number w is s plus it, then z times z conjugate is x squared plus y squared. There's a proof of that below. Let's look at it. So z times z conjugate would be x plus iy times x minus iy, which when you distribute that multiplication out, you get x squared minus iy plus ixy plus y squared, where the ixy minus ixy cancel, and you get x squared plus y squared. Okay? The second thing that's true is z plus z conjugate is 2 times the real part. The conjugation of the sum of two complex numbers is the sum of the conjugates. If w isn't the 0 complex number, then the division of two complex numbers is equal to the conjugate of the division, and a complex number is equal to its conjugate only when that number is a real number. Okay? So I'll probably get you to prove a bunch of these at the next tutorial or perhaps on your assignment. But that should be fairly easy. Okay. So the modulus of a complex number is going to be the square root of x squared plus y squared. So it's we can give it by that statement that the modulus squared is equal to z times z conjugate. And we can see this very easily if we realize that if we draw a complex number on the plane, you have the real part is the adjacent. Yeah, adjacent. I'm going to build a triangle. So we have an adjacent, which is the real part, an opposite, which is the imaginary part. So then the hypotenuse is going to be the square root of the sum of squares of the sides of that triangle. Right? And this is what we're going to be talking about mostly for the rest of the lecture. So this gives us some simpler way or a more compact way to define complex inversion. If we let z be that complex number x plus iy, then we can define 1 over z as the conjugate over the modulus squared, or the conjugate over z minus z conjugate, z times z conjugate. Right? The moral of the story here is to invert a complex number, you just take the conjugate over the modulus squared, right? So that x squared plus y squared part. So here's an example. 1 over 3 plus 2i is the conjugate over 3 squared plus 2 squared, which is 9 plus... Not 16. It's 13. I am just not doing well with arithmetic. That's why I'm more of an algebra guy. I don't care about the minutiae of algebra, arithmetic. Yeah, so the bottom should be 9 plus 4, which is 13, not 16. Okay, so as I was saying, that we could draw complex numbers on a plane. We call this the complex plane. It's sometimes called the Argand plane after the guy who discovered it, or I guess first was the one to use it. So we call these Cartesian coordinates, because that's another guy who invented it. Lots of names here. But the point is that we can take any complex number and draw it on the plane like this. So if you have 4 plus 3i, then it corresponds to that point. Right? Real part 4, complex part 3. All right, so this actually defines the Cartesian form of a complex number. So when a complex number is written in its Cartesian form, we write it like this. Z is x plus iy, where x and y are going to be taken as coordinates from a Cartesian plane. Okay, so once we realize that we can draw these complex numbers, period, we can draw them, we can illustrate some properties of the complex numbers that we discovered last week. So here's u and v. If I wanted to add these numbers together, I would shift one of the numbers up until the other one. Right? This makes sense, right? Because if you want the sum of u and v, you should move v first by the real part of u and then by the complex part of u. And the result here is going to be the sum. Easy peasy. Okay, let's do it the other way. Let's shift u instead now. Give that as the sum. And as you see, u plus v is v plus u. Okay? So this geometrically demonstrates that complex addition is commutative. Right? We can add them in either order. Okay, how can we now take a look at subtraction? Considering that we really haven't defined subtraction on the complex numbers, right? We only know how to add negatives, right? Which functionally is subtraction. So here's u. How should its negation look like? What?
Mirrored without the real.
Should the line be here?
No.
Should the line be here?
Yes.
Should the line be here?
Yes.
No. The answer is no. Should the line be here? Yes. Thank God you guys know the process of elimination. Okay. The reason it lands in here is because when we negate a complex number, you negate both the real and complex parts. So first it will reflect here, and then it will reflect here. Right? Consider the first example we had was 4 plus 3i. It was drawn at 4, 3. Its negation would be minus 4 minus 3i, and thereby it would be drawn at minus 4 minus 3, which is the reflection in that axis, the y equals minus x axis. Okay, so first notice that this proves that u plus minus u is 0. Okay? So we just have to overlay these things. You go up away from the origin and then back towards the origin. Right? So this sort of demonstrates geometrically what we mean by additive inverses. Okay, so if I want to subtract u and v, we're going to see that this is not commutative. Okay, so here's u and v. There's the negation of u and the negation of v. So let's do u plus v first. All right, there's v. I want to add them. There's the result, u plus v. What's next? Minus u plus minus v. All right, that's going to be minus u minus v. What's next? Minus v plus u, right, or u minus v. That's that. And lastly is v minus u, which must be that. Okay? So subtraction is definitely not commutative. Did I do something wrong again?
No, you just made us speak though from the...
Yeah, I'm really hoping none of you would notice that. In fact, I did it first where I put all like the solid lines first and then the dotted lines. I'm like, I just drew a swastika. Maybe I can draw on the dotted lines and they won't notice. Fine. Whatever. It happened. Let's deal with it. Sick minds, you guys. Okay, but notice that none of these are the same line. Right? So subtraction cannot be commutative. We got different results in each case. Well, we do have some symmetry in here, which should be telling. Right? So does this make sense? That u plus v and minus u minus v are like lie in this sort of x minus y symmetry? Yeah, because this is the negation of that. Minus u plus v is minus u minus v. What is that? Same thing here. If I take the negation of this, you get minus u plus v, which is that thing that's over there. Okay, time to redeem yourselves. Where should the complex conjugate lie? Here? Yes. Right? Because we're only reflecting in the complex part, which is the up-down one. Okay? So it's conjugate. So one of those propositions I gave you on conjugates showed that u plus u conjugate should be to the real part of u. If I draw this, damn it, I gave away the answer. Well, there you go. Right? This demonstrates geometrically that that proposition should be true. Right? Because if I draw it like this, you can easily see that we'll get to real part u. Okay. So here's another proposition that I gave you that said that the conjugate sort of propagates over the sum. That is, u conjugate plus v conjugate is u plus v conjugate. So there's u, there's v, there's u plus v. Okay? So what our intuition tells us that u plus v conjugate then should be this line, right? Reflected in the complex axis, or in the real axis. There's u conjugate, there's v conjugate, there's u plus v conjugate. Right, so we're getting a sort of geometric intuition about these algebraic things that we're studying last class. And this interplay is important. Okay. Here's multiplication. Any ideas?
You and then put together and
Yeah, but you knew the answer beforehand. Right? So this is sort of gives us a reason to say, okay, maybe there's a different way we can draw these things, because this really doesn't give us much intuition about the product. How can we get something that's more expressive. Okay, so we know there's another way of drawing points in the plane. So the first way is to specify an x-coordinate and a y-coordinate. Another way is to specify a length and an angle. So hopefully you've all seen polar coordinates. Has anyone not seen polar coordinates? Excellent. In any case, this is a polar coordinate. So we can give a complex number instead by a distance and an angle. So we saw a definition for the Cartesian form of a complex number. Now I'm going to give you a definition of the polar form of a complex number. So the polar form of a complex number is written using a length and an angle like this. So for z, our Cartesian coordinate, we had z is equal to x plus iy, where x and y are from the plane. And now we're going to have r cos theta plus I sin theta. We'll make sense of this. Some more definitions before we continue. So for Cartesian definition, we had the real part of the complex number and the imaginary part of the complex number. For complex numbers written in polar form, we're going to have the modulus of the complex number, which is easier to calculate here because it's given explicitly. And that was x squared plus y squared, root of that formally. And the argument of a complex number given in polar form is going to be this angle. Okay, so the problem with angles, right, as we discovered, well, some of you discovered on the tutorial. If I'm at 1 o'clock on the clock and I add 12 hours, you get the same hour back. Same is true for working on a circle. If you're at some angle and you add 360 degrees, you're back to the same angle. So I like to use radians instead. In fact, we are going to assume from now on that any angles that we're talking about are given at radians. If you're at some angle and you add 2 pi to it, you're going to go back to the same point. So what is the consequence of this for the complex numbers? It means that there is more than one way to write a complex number. This is a problem. Right? So any complex number where you add 360 degrees or 2 pi to the argument is going to give you the same complex number. So generally, we're going to assume that the angles that we're working with have already been reduced by 2 pi. Considering the question I gave you on your tutorial, how can we, what's another way of expressing that? Using remainders. You want to take theta, divide it by 2 pi, and take the remainder. Right, that's going to give you what we call the, did I write that down? Principal argument of z. Right, so when I say reduce something mod something else, that means take the something, divide by the something else, and take the remainder. Right, so pi half divided by 2 pi is 0 remainder pi half. 5 pi half remainder divided by 2 pi is 1 plus pi half. Okay, so in both cases, we reduce and get pi half back. But just keep this in mind, that there are many ways to write the same complex number. And to mitigate that, we're going to insist that the way that we're writing these numbers down have a theta that falls in between 0 and 2 pi. The same reason we wouldn't say, meet me at like 27 hours. Right? You would say 3. Yeah. Or, I don't know, 20. We'd say 3. Okay, so here's some geometric way of explaining the correspondence between Cartesian numbers, Cartesian complex numbers, and polar complex numbers. Okay, so if we have z, the same z, this is its real part, this is its imaginary part, and its hypotenuse is given, of course, by the square root of x squared plus y squared, which we've already defined to be the modulus. If the argument of z is theta, then we know that the length of this is the modulus of z sine theta and the modulus of z cos theta. So this diagram should be enough to convert one through the other. So in fact, the statement on top is the correspondence between complex numbers given in Cartesian form and complex numbers given in polar form. So it should be noted, if I give you a complex number, it is written both in Cartesian form and complex form, right? Despite whether or not you see cosines, sines, or angles. I can ask you the same question either way. I could say, here's 2 plus I. What is its argument? Right? And you have to go from the left of this equation to the right and pull out theta. I could also ask, what's the real part of cos pi half plus I sine pi half? And you'd have to convert back to get those. Right? So if you're in the course underneath here, we'd spend 20 minutes going through examples of this, but I leave it up to you to go and practice. So we'll give you some problems to work out. But it's the important part is to realize that just because the number doesn't have sines, thetas, does not mean that it's not a polar number. Okay, so here's a proposition. A complex number satisfying z is equal to r, some real number. Form a circle of radius r in the complex plane. Okay, and we're going to endeavor to work this out. I want this. Okay. The point satisfying z equals r, a real number, form a circle in the complex plane. Okay, so how do we start this? Okay, so let z be equal to x plus iy, which is a complex number. This means z equals r if and only if x squared plus y squared square root is equal to r. This is by definition of modulus. This implies x squared plus y squared is equal to r squared. So points satisfying star form a circle. Okay. Where's my phone? Oh, thank you. Okay, so I'm saying, show me that the Cartesian coordinates satisfying the modulo of z equals r form a circle. Okay, well, this is sort of easy. If the modulo of z is r, this means by definition that the square root of x squared plus y squared is r, and if we square both sides, we get x squared plus y squared equals r squared. So any point satisfying this will have modulus r, and you see that's that. Very deep. Okay, here's a couple of things you could try to prove at home. That the modulo of z times w is equal to the modulo of z times the modulo of w. And the argument of z times w is equal to the argument of z plus the argument of w. In fact, we may try a couple of these because we're super early. And for complex numbers w, the division of z by w, modulus, is equal to the modulus of z over w, the modulus of z over the modulus of w. And the argument of z over w is equal to the argument of z minus the argument of w. So actually, let's try doing, which one of these do you want to do? All right, fine. Which translates to, we don't want homework. Okay, so I'm breaking the cardinal rule of teaching. You should never attempt to do math in front of an audience. It's always doomed to failure, as you saw last week. Okay, so maybe I'll get you guys to walk through this with me. Just let me pull up a question.
Would you like some more paper?
Okay. Proposition. For two complex numbers, Z and W and C, we have 1. That the modulus of ZW is equal to the modulus of Z times the modulus of W, and the argument of Z times W is equal to the argument of Z plus the argument of W. Okay, so let's start this. So I have to show you guys how to start doing proofs properly. Okay, so what's the first thing that you reckon? Yes. First one is say let Z is equal to, what did I write here? Well, should we do it in, we should do it in polar, yeah? Yeah, okay, so R cos theta plus I sine theta. And let's write W as S cos phi plus I sine phi.
Can we shortcut that by going to use the I theta?
That uses Euler's formula, which we'll be studying next week. Yeah. So yes, but no. It's a shortcut only when we derive Euler's formula, which is hardly a shortcut, right? Because you need that result before you can use it as a shortcut. This will be much shorter than demonstrating Euler's formula is true. Okay, so I guess we just go through this the hard way. So what is Z times W? Okay, so Z times W is going to be, well, let's do this. Let's skip a step. So we have R times S times cos theta plus I sine theta times cos phi plus I sine phi. Okay, so now let's work out the cross terms. So we get cos theta cos phi plus I sine theta cos phi. I did this and this and this and this. I already screwed this up. Yeah, I usually do it in different ways. So I did this and this and this and this. So I need to do this and this. Okay, plus I cos theta sine phi plus I squared sine theta sine phi. Okay, so what is this? This is R S cos theta cos phi minus sine theta sine phi plus, I'm going to factor out the I, cos theta sine phi, and then sine theta cos phi. Okay, who remembers their trig identities? two-angle formula, yeah? What's cos theta plus phi? Blah, blah, blah.
It's cos theta cos phi minus
Okay.
sine theta.
What's cos theta plus phi? So,
Cos theta cos
yeah, I know I'm spoiling the surprise, but okay. Minus.
isn't it cos cos and sine theta? You're doing sine theta minus theta.
Yeah? Okay. Which means this is cos theta plus phi. Jesus. So what's this? Okay. Okay, so what is the modulus of z times w? So we wrote it like this. Yep, r times s. Check, right? That's what we wanted to prove here. What is the argument of z times w? What's the argument? Which is equal to the argument of z plus the argument of w. Yeah, so proved. That little square means. Quandes demonstratum, as I have demonstrated. So it always denotes the end of a proof. Okay, so I'll let you do the other one at home, and we'll just sort of discuss something for 5 minutes. I'll let you go a little bit early today. Is the next topic. There's no point going into it in the next 20 minutes. Okay, so something to think about. For next class. We're going to be talking about something called Euler's formula. Okay, which is this statement. Okay, and it turns out that R, E, I theta is equal to R cos theta plus I sine theta. Okay? Where, so note, ln of E is 1, right? And who remembers what the derivative of ln x is? Yeah, 1 on x, x prime. Okay? So using these and the cosine rules, like cosine rules, you already have enough tools to prove Euler's formula. So like, why don't you give it a try? It's going to be challenging. You're going to have to make an inspired guess. Maybe I'll tell you the inspired guess. And these are known as magic steps in the math circles. It's that cos theta plus I sine theta is equal to x theta. So from that, you should be able to deduce Euler's formula. So is there any questions? Okay. Get out of here.
When you were talking about the relationship between the function and the you said C plus C and
Two real participles.
why didn't you say the negative C minus C is equal to imaginary C?
Is that true?
So, saying that conjugate of E minus
C minus 1.
Yeah, both would be true. I guess it must be the same picture.
Yes.
Yeah. There are some things that aren't true. Like demonstrate, for instance, that the imaginary part of Z times W isn't in general equal to the imaginary part of Z times the imaginary part of Z. Some things that look like they should be.
Not right.
So suppose I made B the empty set. And you're saying that A minus C is equal to A union A minus C. Okay. So this can't be true.
Do we always use that bound? Not always use that star.
In this course, we'll be using the notations in error.
True if it's not prime number.
I can't prove that off the cuff, man.
I can prove it.
Exceedingly close to format close. Prove that this isn't prime. So I suppose but this isn't true for 1. 1 times 1 is 1 is equal to 1. And 1 plus 1 plus 1 plus 1 is 4, and that's constant.
So 4 is not prime number.
Oh, so that this is always composite. Right? So if this is true and this is true, then this implies isn't prime. Right? Yeah,
I've got a pair of shoes like that, except they're red.
No way I can
You must be a queen.
But I would suggest that you try to say that if this is prime, then this can't be true. So like there is no way to. Yeah, I don't know. I don't know. Probably not. Yeah, I can't do it like off the top of my head. So this is probably what you're reading for.
Yes.
Thank you.
Are you doing the tutorial on Friday?
No, I do it on Tuesdays.
So this is straightforward if you use the balancing respect. But what?
Can you do it like this? Though?
Yeah,
An elementary proof
A
of
bit
it.
more hint on this one and also.
Yeah, that's basically. Well, you want to use the inspired guess, like start taking derivatives and stuff.
Obvious, but yes.
That's a good place to start. If you get really frustrated, you can just look it up. Right?
Well,
it's fun. These kind of things are fun to play around with.
yeah, I've seen the table figures on many times. I can do that.
Yeah, but then we need to have resultants. So this is the difference between algebra and calculus. Like we have a set of finite amount of things that we have shown to be true, and we are only allowed to use these things to show that other things are true. So I guess we're cheating by using derivatives, but I could easily write out the rules for calculus. No problem. I have no idea. This is the first time I've taught a class here. Like I've only been here for like half a year. You may ask someone else in the. Like, do you know anyone in the grade above? So like you'll certainly come out of this a better problem solver. So it all depends. Like, what's your goal? Is your goal to like maximize your marks? Is your goal to like set yourself apart from the rest of your colleagues? Yeah.
How argument you said before, you said it's between 0 and 2 pi. I thought that was between negative pi and pi.
Okay, but then we have to use negative numbers. I like this way.
I feel like you have to. That's just, no.
If we define it between them, then we're going to have negative arguments.
Yeah.
Right, so forcing it to go between 0 and 2 pi means that we'll always be adding things.
So if I were to...
It's exactly equivalent.
Yeah, but like if I were to use...
I wouldn't mark it wrong. Yeah. No problem. Yeah.
I guess if you use the unity side, it would imply that that means 1 over e to the right.
Yeah, it'll screw things up a bit. Yeah.
Just a comment on the notes. I guess for me personally, it would be useful if you had a report. You know, even if there's mistakes.
Yeah.
I would then I could correct them as we go, and I'm worried that being so old that I would forget. But you know, if they're printed it out.
So like this is the thing that like I've sort of been instructed not to do this, so people come to lecture, even though this is sort of pointless because I know I post them afterwards.
So you just post them straight away?
Well, I'm gonna work on them a bit today. So like the thing is, the lecture informs how I'm gonna write them later. I get a sense of like what was clear to everyone, what requires more explanation.
Yeah.
So really, like the notes that I'll be giving you would just be like an enumeration of like the.
Are you putting these on Echo then as well?
These are on Echo.
Okay.
Yeah.
Because I was just worried that if I got it, you know, in a day or two, I would have forgotten what was there.
Yeah. So I usually post them pretty promptly. But again, I find that writing these notes after the lecture is better because it informs me how to write it. Yeah.
All right. Thank you very much.
Yeah. Thank you. Hey.
Hey, yeah.
Oh, you're just copying.
No.
Oh. Did any of you have questions?
Yeah, questions.
Sort of hang.
So yesterday we both went to a physics pass session, and we had a student in third year give us an email afterwards telling us that there's other courses we could do like now. So we've both just enrolled in analysis yesterday.
Okay.
And I don't know. Do you think it's like feasible to catch up and doable at this stage? Like it would only like 3. Like
To catch up in analysis?
Yeah.
What level is it?
23.
No, I don't feel any reason that you shouldn't be able to do it. It's not like they're using information that you've been given previously. You're just going to be doing exactly the same stuff that we're doing, but like more in depth.
Yeah.
So this may like totally invalidate like all the classes you're taking with Dr. Rohr. I'm surprised these aren't anti-requisite. Have you checked that?
Yeah. Well, it says there is.
So the requisite can be either this course or high extension.
Yeah.
No, I meant anti-requisite, as in if you're taking that course that you're
it
not
says
allowed
that.
to take this
Since
class.
it says if you're enrolled in 1210 and you've got a high result in extension 2, how you accept into it, you can go into it.
So I found analysis really difficult.
Yeah.
There's like this is when you branch into mathematics, it's like statistics applied pure. And then once you go into pure, there's like another great divide where it's like those people who like algebra better and those people who like analysis better. And I happen to branch on the left. So I found analysis extremely difficult.
Yeah.
So keep that in mind that when you're taking this course, that it may be quite difficult.
Yep.
But yeah, I don't see any reason why you shouldn't be able to do it.
Yeah, cool.
Guys seem
So
clever
on
enough.
Blackboard, you were on the list of instructors for the
Analysis.
330 class.
Oh, I was listed as a tutor.
Oh, yeah, okay.
That's no longer the case.
Okay.
Yeah. I don't know. Yeah, there's a lot of. They sent us at least like half a dozen tutorial allocations before it like stabilized.
Yep.
So I guess Brayley's teaching that.
Yeah. Yeah, sent him an email. He was pretty encouraging. He said, yeah, it's all good. Just come in on Friday and it'll help us out. Just help us
Yeah,
catch
you've
up.
only missed like what, like a couple lectures.
Yeah, 3 lectures.
Yeah, you should catch up. I don't know. I didn't really take much from lectures when I was a student, anyways.
Yeah, cool.
Okay.
Awesome. Thanks, heaps.
Good luck with that.
Thank you.
I'd like to know how much mark you give me for this.
What are you trying to do?
There is a question say, prove that limit doesn't exist when x approaches to 0. Suppose then I put epsilon as 1/2.
Okay, so you're using the wrong. This is not indictable, but you should be using this as epsilon.
Oh, okay. Oh, sorry, yeah.
Yeah. Prove that the limit doesn't exist. Let x be. Okay. Why are you setting it to a number?
Because like if you put x as 2 pi plus pi over 2, that's 1 because it's 90 degrees.
Okay.
And then the denominator would be 1, the whole sine x. The value of the function would be 1.
Like, what does this have to do with angles, right? So 1 over x is this.
Yeah.
So you can very easily prove that the limit doesn't exist. We'll prove because the limit from the top
Yeah.
is positive infinity, and the limit from the bottom.
Ah, hang on. That's sine.
Oh, scheisse. Okay, yeah,
Sorry.
that does. No, I apologize.
Yeah, I should have.
No, it doesn't. I didn't see that. Well, it's because 1 over x is infinity. So like sine for any x
Yeah.
is always less than or equal to -1 and 1.
Yeah.
Okay? Which means that we're asking what the value of sine is at infinity. And all we know is that it's sort of in between -1 and 1. So to prove this formally, I suppose, you would have to paper. Suppose limit of x goes to 0 of sine 1 over x is equal to L,
Yeah.
for L is some number.
Yeah.
Right? You don't get to choose.
Well,
They get to choose, right? Because you all you've done is prove that it can't be that.
Yeah.
Okay? So you have to say, suppose it's set.
Yeah.
We've set it to something.
Yeah. I tried the contradiction to suggest the thing that doesn't work.
Yeah.
Therefore, the theorem wouldn't work because it would be easier than not contradiction. Oh, what was that?
That's a little bug.
Oh.
Stick bug. So this is from the tutorial, yeah?
Yeah.
So we're not actually asking for like a proof, at least at this
Yeah.
point.
Yeah.
We just want you to
Like
demonstrate that you have an intuition about these problems.
Okay.
So I can show you. So we're just looking for something along the lines of sine oscillates between -1 and 1.
Yeah.
So at infinity, all we know about it is that it's going to be between -1 and 1. So it can't have a limit.
Can I just explain what?
Yeah, something like that. But the other one doesn't.
Is there any?
Yeah, you'll have to ask Dr. Willis about that.
there's some sign. Yeah? Do this. And we're investigating the limit at 0, which means I want to look really closely at 0. So I'm going to divide these both by x. So that's what it looks like locally.
Yeah.
So you see all it like
Oscillates.
yeah, like it's just going to do this at 0. Like no matter how close you look like, it's going to have an infinite amount of more oscillations before. Right? Unlike the other one, this. If we look at this very close, that would have it's doing this. Which means that for any epsilon, we can bound it. Okay? Which isn't true for the other one. Because the range is always between -1. Yeah, but your central mistake here is that you're not allowed to pick. You are only allowed to say it's set. Okay, so give me an L. Give me any L that's fixed, and I can demonstrate that that is not but yeah, we're not asking for a proof on the now.
I would say it oscillates more. Because it gets to 0.
Yeah, you just
So
go.
therefore it would.
Like it's equivalent to asking what the value of sine is at 50.
Right.
And then it just goes up and down like this.
Yeah.
Right, so the other one just proves something is like this. Right? So you want the limit,
This one.
yeah, as x goes to 0 of x times sine.
Yeah.
So you learn that this limit distributes over the product. So this is equal to limit as x goes to 0 of x times the limit of x goes to 0 of sine 1 over x. So we know that this is a number between -1 and 1. We know that this is 0. The only thing we can't multiply by 0 is infinity. So this is we don't know. But since this is always finite, 0 times it is always 0. So that's sort of a proof of how we do it.
Oh yeah, that's really good.
Yeah. No, you can just use one of the front. Right, but it is interesting to see that if you look at sine 1 over x. Say that the limit of x goes to 0 is equal to L, and use the strict definition. And show that this fails. And say, okay, so you do it, say if and only if this. Say set L in R and epsilon greater than 0. Then show there does not exist delta satisfying.
It will be really hard to do the algebra calculation along the way.
I don't think it'd be that hard, because you just use the fact that sine oscillates, right? You can show, okay, if they pick an L, just say, well, okay, let's go a little bit further out, then it won't be this value of L. Because if you go too high out of L, you know that any point on sine is separated by I can get at least, so if you go epsilon up, you're this far away from the x-axis. But sine, I know I can get the negative value of it. So look, you can always make a range that's bigger than the thing that they're trying to be smaller than. If you Google it too, I'm sure.
Yeah, I'll put it.
So it's interesting, but at this point not necessary yet. See you.